Yes, so as we remarked, we have three equations. The equation for the conservation of mass flux, the equation for the conservation of momentum flux, this one, and the equation for the conservation of energy flux, which is this one. We have three equations and six unknowns: two densities, one upstream, one downstream, two pressures, one upstream, one downstream, and two velocities, one upstream and one downstream. And if you think that we are introducing a new quantity here, enthalpy, it's not really new. It can be quickly related to the pressure and density like this, right? So, and enthalpy relates to the internal energy per unit gram, of course, the internal energy of the fluid, whereas this half u squared relates to the energy of the fluid due to the bulk motion. Okay, so and it's important to add them together, and so this represents energy conservation. So we are now ready to start talking about things like U1 over U2 or rho 1 over rho 2, and these are the jumps, or rho 2 over rho 1 as the case might be. But remember, these refer to jumps in normal quantities, normal to the shock surface, not tangential. For instance, normal velocity, there's no sense in talking about normal. I mean, this is just density. So normal quantities, e.g. velocity, normal velocity. Okay, so let's jump right ahead and let's define the Mach number of the shock as U1 over CS1. Okay, so this is just by definition. We could even have defined another Mach number, which would be U2 over C sub S2 with respect to the downstream quantity. This is just convention. Okay, it is easy. I mean, it's conventionally one speaks of the upstream Mach number. You should more correctly, it should really be talking should really be saying upstream. Okay, so this is the upstream Mach number of the shock, and so that's the definition. And using this and using those three equations that we showed in the slide, we can show that, and I strongly urge you to do the little bit of algebra that's needed to show this. You can show that rho 1 over rho 2 is this quantity. Gamma is just the adiabatic index, right? And so it can be 5/3 or 1 as the case might be. And so all, as far as the fluid is concerned, so gamma is a constant. That's what I want to emphasize. Gamma is simply a constant. So as far as the fluid is concerned, what is the quantity that characterizes the fluid flow? There's only one quantity, and that is the Mach number. Okay, so it's the only thing that appears in the jump condition, and it is inversely proportional to the Mach number. So the larger the Mach number, the smaller the density jump, right? The smaller the Mach number, the larger the density jump. That's what this equation is telling you. So this is the density jump condition. Equivalently, you can also, once you have the density jump condition, you can immediately find the pressure jump condition or the jump in velocity, in normal velocity, mind you. Okay, it's very easy to show this, right? And this is the plot. This is a general, so everything and all of these functions of only the Mach number m. The Mach number m is the only thing that matters. Okay, the Mach number does not explicitly appear in these equations, but you can play a little bit and recast these equations in terms of the Mach number. Okay, and you'll find that this is how it appears. Okay, and this is the plot. So since these ratios are functions only of the Mach number, and so the Mach number m. So the Mach number is plotted on the x-axis and the ratios are plotted on the y-axis. The ratio, the pressure jump ratio, the temperature ratio, or the jump in the sound speed, or the jump in the density, all of these are plotted on the y-axis. Okay, specifically the log of the ratio is plotted. Okay, so here it would be, the ratio would be 1, here it would be 10, here it would be 100, here it would be 10 raised to minus 1, and so on and so forth. Yeah, so what are the main things to be noted here? The first curve, this is a rather busy graph, and in this particular case we have taken gamma to be equal to 5/3. Need not be the case. You can take gamma to be any other number, but this particular graph is plotted with gamma equals 5/3. So let us first look at the density jump. This curve, which represents rho 2 over rho 1, this one. What does this show? This shows that the ratio of the downstream density to the upstream density increases with Mach number. It increases a little bit, right? So, and then it plateaus off. Beyond a Mach number of about, shall we say, this is something like 4 here, this one. Okay, this is a Mach number of about 4. So beyond this, okay, the density jump pretty much plateaus off. Okay, maybe not 4. Okay, so this is about 5. So yeah, something like the 4. Okay. So what this is saying is that beyond a Mach number of about 4, it does not matter how much stronger the Mach number is, the density jump remains the same, and the value for that is something like, well, it's hard to read off a log scale. Okay, so whatever this value is, and you'll find that the velocity jump, this one, this looks like a flip of the density jump ratio, and indeed it is, because remember rho v or rho u, rho v is constant. So in other words, rho 1 over rho 2 is equal to v2 over v1. So if you're plotting v2 over v1, it's exact opposite of rho 2 over rho 1, right? And not surprisingly, this also exhibits exact same behavior beyond a certain Mach number. Okay, the ratio plateaus off, except this ratio is smaller than 1. Remember, this is 1, so this side is larger than 1 and this side is smaller than 1 because it's a log graph, right? So it plateaus off beyond about Mach number of 4. What this is saying, I mean, the way people express this term, this is to say that beyond Mach number of 4, you can effectively regard this as an infinitely strong shock. It's a bit misleading, this terminology, an infinitely strong shock. It's not saying that the shock strength is actually infinite. In other words, the Mach number is actually infinite. No, it's not saying that. Anything larger than 4, anything that larger than a Mach number of 4 is effectively infinite. Okay, as far as the density jump and the velocity jump are concerned, it does not matter whether the Mach number is 5 or the Mach number is 100. It's the same result. So that's why people normally say Mach number is an infinitely strong shock. Okay. So, I don't want to belabor this thing. So, this is how the the ratios look like for the density jump and the velocity jump. The downstream Mach number m2 also looks very much like the velocity curve. Okay, this is the downstream Mach number. What's plotted on the x-axis is the upstream Mach number. Okay, so everything is written in terms of the upstream Mach number. So the downstream Mach number looks like this. You increase the upstream Mach number, the downstream Mach number reduces. Okay, so the flow is transitioning, and they say all over here, because you're lower than 0, you're basically saying that the quantity is less than 1. Okay, so this is the log of the downstream Mach number, right? So it's less than 1. No surprise. What the shock does is it takes a supersonic flow, okay, and turns it into subsonic flow. That's why all over here, the m2 is less than. The sound speed, the cs2 over cs1, this is the sound speed ratio keeps increasing. It keeps increasing. There is no plateauing of the sound speed ratio, but the increase is quite gentle with increasing Mach number. By Mach number, we mean upstream Mach number. Similarly, this is the ratio of the temperatures, T2 over T1. This is the ratio of the pressures, P2 over P1. All of these, once you know rho 2 over rho 1, which is what we've written down here, or rho 1 over rho 2 equivalently, it's the same thing. You can immediately write down P1 over P2, T1 over T2, V1 over V2 is just the flip. Okay, so to emphasize, right? That's why this and this graph, they look like flip versions of each other. The other thing to say is that often there's another name, these shock. We've simply said shock jump conditions, but if you look in books, these are called Rankine-Hugoniot jump conditions. Same thing. Okay, this is the name. Named after the two scientists who pioneered this field. Okay, so these are the Rankine-Hugoniot conditions, and this graph gives you all the information there is to need. So I urge you to stare at this in detail and think about it. Okay, and the other thing we said was essentially any Mach number above 4 is essentially an infinitely strong shock. It's not like the strength of the shock is infinite. It's just that anything above, as far as the density jump and the velocity jump, which are the two main jumps, that are often considered, as far as the density and the velocity jumps are considered, anything above 4 does not matter. Okay, the Mach number can be 4 or 100, is the same jump in density and velocity. It's in that sense that shocks with Mach numbers greater than 4 are called infinitely strong shocks. So I just wanted to emphasize that a little bit. Yeah, so this is what I was just saying clearly. Well, not just the ratios, the density and velocity ratios. It's not the reason I said this is because you can see that the pressure and temperature ratios and other things, they don't plateau off. It's only the density and velocity ratios, they plateau off at large Mach numbers, right? And you can see this just from the expression. For Mach numbers much larger than 1, rho 2 over rho 1 is just a constant, and this is exactly this plateau. It's just a constant. There's no Mach number appearing here. Why is that? You look at this. You look at the expression here. When the Mach number becomes much larger than 1, this term is negligible. So, this goes away, all you have got is gamma minus 1 over gamma plus 1, that is it. So, that is what this is saying. There we are rho 1 over rho 2, whereas here we are writing rho 2 over rho 1, that is why this is also flipped. There is no Mach number dependence anymore. And if this is rho 2 over rho 1, this will be equal to, this will naturally be equal to V 1 over V 2, same thing, right? Yeah, it is just a flip. So, I beg your pardon, sometimes I write V, sometimes I write U, it is the same thing. It refers to the fluid velocity, and the reason is simply, just to show you once again, it is simply because of the way this term appears when Mach number is much larger than 1, this term is approximately equal to 0, right. So, for the time being I will just erase this, is not so important. If I can find the eraser. Anyway, I mean, so this is for, I should say, for very large Mach numbers, this is essentially equal to 0. Okay. So, that is what this is saying. Does it make sense? Of course, it makes sense, right? Because right, that is why this is the flip of that. The ratio of the pressures, okay, is essentially you can write P equals NKT, okay, or you can go back to the basic conservation equations and derive this again. The ratio of the pressures looks like this. It does have a Mach number dependence. That is why the pressure ratio, you remember this? The pressure ratio keeps increasing with Mach number. It does have a Mach number dependence, and that is reflected here. Okay. And all these are, all these hold only for Mach numbers much larger than 1. Okay. And generally just means as long as you are above 4, you are essentially an infinitely strong shock. Generally that is what it means. Okay. So, I wanted to emphasize this because generally you would say, well, Mach number, any quantity in physics, if you want it to be much larger than 1, it has to be larger than at least 10. Okay, it should be something like 100 or 1000, only then this kind of a thing. In this particular case, that is not so. That is why I am saying it. If you are above 4, above something like 4 or 5 or something, you are already in this much larger than 1 regime. Okay, I just wanted to emphasize that, and you can see that from the plateauing of the density ratio and the velocity ratio. Okay. So, now having talked about shocks and these interesting things, we now start talking about what are called transonic flows. Transonic flows essentially means a transonic flow is one that transitions from Mach number less than 1 to Mach number greater than 1. Okay. Of course, through Mach number equal to 1, naturally you are transitioning from a subsonic flow, which is Mach number, sorry, very sorry, it is not this. Yeah, Mach number less than 1 to Mach number greater than 1. So, this would be a subsonic flow, right. So, a transonic flow is one which transitions from a subsonic flow, which is Mach number less than 1, to a supersonic flow, which is Mach number greater than 1, through Mach number equal to 1. Naturally, you will encounter Mach number equal to 1 while transitioning from a subsonic flow to a supersonic flow. Yeah, and these are called transonic flows. The reason we pay attention to this is because, as we have seen, the character of subsonic flows and the character of supersonic flows very, very different. Very subsonic flows are essentially quasi-hydrostatic. Pressure gradients and pressure differences and boundary conditions play a very vital part. Supersonic flows, on the other hand, are essentially ballistic. Boundary conditions really, they don't care about boundary conditions. And so the character is very different. So while transitioning, one has to pay special attentions. I mean, it's one thing when we are dealing with entirely subsonic flows or entirely supersonic flows. Certain terms can be neglected and you can go on with the analysis. However, as with any thing in physics, when you are dealing with transonic flows or flows that straddle these two asymptotic limits of subsonic and supersonic, when you're straddling these two limits, you have to be a lot more careful. Okay, right. So these are what transonic, and in particular we will pay attention to transonic one-dimensional flows. In other words, say just the x dimension, y and z are not important. Yeah. So why are we discussing this? Because why are we discussing this in an astrophysical fluid dynamics class? Because transonic one-dimensional flows are essentially of great importance in understanding things like astrophysical jets. But before talking about astrophysical jets, let us talk about an engineering application because these things are much better established in the lab, and then we will go on and apply our understanding to astrophysical jets. Okay, right. So we already know something about, so let's talk about flow through a pipe, a transonic flow through a pipe. Okay, we already know something about this. In fact, we use the same kinds of equations. We write mass conservation in the following form: rho A U equals constant, where A is the cross section, A is the area of the pipe, which we allow to vary. A can vary with x. You can transition from a thin pipe to a thick pipe. This is the main thing, right? And what exactly does this represent? You see, again, dimensional analysis, rho is something like grams per centimeter cube, and A is an area, therefore it's something like centimeter squared, and U is centimeter per second. So what this is essentially saying is that this is expressing not the conservation of mass flux, but the conservation of a quantity which is grams per second. We call both mass conservation. We call, earlier when we were talking about shocks, we called conservation of mass flux just mass conservation. In this case, we're still calling it mass conservation, but we are really conserving grams per second. That's what we're doing here. Okay, rho AU equals constant, where A is a cross-sectional area of the pipe, which is allowed to vary with x. Okay. The other thing is the Bernoulli constant, which is essentially an energy conservation equation, and that can be written as this. This is slightly different from the way we were writing it earlier, but it's essentially the same thing, where Cs is, of course, the sound speed, which is allowed to vary, which can vary. Okay. Yeah. So now the question we ask, just based on these two equations, how does the flow behave in a diverging or a converging channel? A diverging channel would be one that looks like this. This would be a diverging channel. A converging channel would be one that looks like this, a nozzle. This would be a converging channel. And of course, clever people would put these two together. You would have a channel that converges, goes through a throat, and then diverges. But before that, let's try to understand how a transonic flow would behave in a diverging channel, how it would behave in a converging channel, right? So let's try to understand this. instead of writing rho AU equals constant, how about writing it down like this? This, I emphasize, is the same as can you see how this is so? What you do is, you differentiate both sides with respect to x, right? And so this is just the chain rule. And you divide everything by rho AU, both sides. When you differentiate a constant with respect to x, you get 0. So that's how you get this. Okay, it's the same thing. Rho AU is equals constant is the integral form, and this is the differential form. The differential form is more useful to us. Okay, right. And the differential form of the inviscid momentum equation, we don't bother about viscosity. We are not concerned even with shock thicknesses or anything. Okay, we are concerned about flows that transition from subsonic to supersonic, not via a discontinuity, not via a shock, but smoothly. Okay, and even when we were discussing shocks, we neglected viscosity, so we neglect viscosity here too. But it's important to realize that we are considering shockless flows, flows that transition from subsonic to supersonic without a shock. This is also something that you should keep in mind. Not all transitions from subsonic to supersonic, in other words, from Mach number less than 1 to Mach number greater than 1, need to go through a discontinuity, i.e. a shock. They can be smooth, and that's the kind of thing that we're talking about here. So that's the differential form of the inviscid momentum equation. We combine these two using the familiar sound speed. We combine this. Again, I strongly urge you to show the following result, this result. Okay, and this is a very important result. Okay, so this would be the way the velocity changes, this would be the way the area changes, the area of the tube. So dA dx, you see, for instance, consider a converging channel like this. So, and if this is x, in this case, you see the cross-sectional area of the tube is large here and small here, isn't it? It's large here and it's small here. So, in other words, in this case, dA dx is less than 0, and its opposite, dA dx would be larger than 0 for a diverging channel. In this case, for a converging channel, dA dx is less than 0. That's what it would be, right? And yeah, so let's sort of look at this equation and try to see. There's a lot hidden here, okay, and this is a very important equation, and there's a lot hidden here. So, repeated that equation here. Consider subsonic flows. Consider flows that have Mach number less than 1, in other words. Right? Consider this. So, when dA dx is less than 0, in other words, a converging channel, as we sketched in the last slide, is du dx larger than 0 or less than 0? Let's just look at this equation, right? So, Mach number is less than 1, which means that this is negative. M square minus 1 is, yeah. So, and then the A itself is always a positive quantity. The area itself is always a positive quantity, isn't it? So, and the dA dx is less than 0, right? So, say the Mach number is 0.1, right? 0.1 times 0.1 is 0.01. So, 0.01 minus 1 is always negative. And what we are saying is that dA dx is also negative. Everything else is positive. So, the negatives cancel each other. So, is du dx going to be greater than 0 or less than 0? Right? Obviously, it's going to be greater than 0. And this conforms to intuition. You take a garden hose pipe, right, and you pinch it. In other words, you decrease the area and you find that the speed of water coming out from the nozzle, okay, is larger, right? You take a garden hose and you pinch it. In other words, you make it a converging channel like this, and you find that pinching it makes the water squirt out. Water squirts out fast. In other words, the flow accelerates. So this conforms to intuition when the water flow is subsonic, and in everyday situations, of course, the water flow is subsonic. It's very much, the speed of the water flow is very much lower than the speed of sound. Okay, so subsonic flows do conform to intuition, and the opposite can be said if dA dx was larger than 1. If you consider a diverging channel, you have a fast flow, and as soon as it encounters a diverging channel, it slows down. The du dx would be less than 0. So this is what your intuition tells you. But what about if Mach number is larger than 1? What about supersonic flows? In that case, what happens is this quantity is larger than 1, right? And the entire thing gets reversed. If dA dx is less than 1, now you see, now we are considering supersonic flows. Now we are talking about supersonic flows. So this quantity is always positive. Once this is positive, if dA dx is negative, then du dx is also negative. It's forced to be negative. If dA dx is negative, in other words, if it's a converging flow, du dx is forced to be negative. So for supersonic flows, what we're saying is that if the flow here was supersonic, you pinch the nozzle and the flow actually slows down. Very strange. Does not conform to intuition. That's the reason we're talking about it here. Okay, and in a diverging nozzle, if you have a diverging nozzle and you have a supersonic flow, the flow actually accelerates. Du dx is actually greater than 0. So this is very strange. Yeah, so for Mach number greater than 1, the signs of dA dx and du dx are the same. So a supersonic flow decelerates in a converging channel and accelerates in diverging channel. This is really something strange, and this does not conform to intuition. And so when you are transitioning from Mach number less than 1 to Mach number greater than 1 through, when you're going from the subsonic regime through equal to 1 to when you're going from a subsonic regime to a supersonic regime through the sonic point, so to speak, that's when Mach number equal to 1, you have to be very, very careful. And this is an example of what's called de Laval nozzle. And so you can marry these two kinds of converging and diverging channels together to get some very interesting behaviors. And de Laval nozzle, the concept of which is just this. A converging channel, welded to a diverging channel through a throat. Okay, and so it really matters whether this flow is subsonic on this side or supersonic on this side. The behaviors will be very, very different. And so this was used for engineering applications, and specifically, for instance, for rocket thrusters, okay, where if you want the flow to accelerate, if you want a large momentum thrust on the rocket, and you already know that the exhaust is supersonic, then you want a diverging nozzle at the end of the rocket so that the flow accelerates. Okay, and so this was really the concept of the de Laval nozzle was really thought of and studied extensively in such engineering applications. But as we will find out when we meet next, it has important applications in astrophysics as well, in trying to understand astrophysical jets. So that's it for now.